I'll start this video by looking a little more closely at the types I used in the last video's code. I have the project file exceptions loaded. Take a look at the import statements in this code. You can see a mix of types, some in the java.io package and some in the java.nio.file package. That looks like a confusing mix, I'm sure. Let's first look at these types on a couple of slides. Here are the two in the java.io package. The file class and the file reader class have been part of Java since version 1. The file reader class implements the auto-closable interface through its parent class, reader. This class opens a file resource implicitly. I'm going to be covering this type and others like it in a later section on reading data from files. In contrast, when you create an instance of a file, you aren't actually opening that file. Instead, you're working with something called a file handler that lets you perform OS-like operations. Let me get back to the code and examine this class. The first thing I want to do is remove the call to the test file to method. I'm also going to remove that second println statement in my if statement. Now that I've gone through the try with resources catch block, you might be wondering why I didn't use it here when creating a new file instance. Not only that, but I also didn't have to wrap anything in a try catch block for this bit of code at all. Getting an instance of a file handle isn't the same as getting an instance of a file resource. That's confusing, especially since the terms might be used interchangeably, but in this case the difference is important, so let me explain it. A file handle is a reference to a file that is used by the operating system to keep track of the file. It's an abstract representation of the file, and it does not contain any of the actual data from the file. A file resource, on the other hand, is the actual data from the file. It is stored on disk, and it can be accessed by the operating system and by applications. In the case of the file class, we're only ever dealing with a file handle, so we don't open or close this. With that in mind, let's look at this class. You can see I was able to create a new instance of it using new, and the constructor, which takes a string literal. This string literal represents a path name. A path can include a file name, as this one does. In fact, this path only includes a file name. I could add a directory or folder here, and I'll do that. Starting with files, then a /. I'll use IntelliJ to create both this directory and this file, so I'll open the project pane and select new file and enter the same thing I have in my string literal. This will create an empty file named testing.csv in a folder called files in my project directory. For now, I'm not going to put anything in that file, so I'll just close that tab. I'll run this code now. I'm good to go because the file was found in the place we specified it would be. How did our program know to start looking in the project directory of this project? That's because I used what's called a relative path. All this means is that my string literal here did not include characters that said start searching for the file at the root location of the disk. I'll explain this in just a moment. First, let's get the current working directory, which is the directory where the application process is running in. Many of you may be familiar with pwd, a Linux command, for displaying the current working directory. Mac also has pwd, and for Windows you can just type cd in a command prompt. For Windows, the current working directory is usually included in the prompt itself. In fact, if you open a terminal session in IntelliJ, you can see this. But let's get it programmatically, using the file class. I'll print out the current working directory, or CWD in parentheses, is equal to. Then I'll instantiate a new file and pass it an empty string as the path. Then I'll call getAbsolutePath on that instance. Let's review the output. You can see the project folder printed there. Yours, of course, will be different from mine. A relative path just means the path is relative to the current working directory. An absolute path, on the other hand, means the path is starting at the root directory. How do I know what my root directories are? There is a static method on file called getRoots. I'll call this in a for loop at the end of my main method. This method returns an array of file instances. I'll print each file that's returned running this code. You may get a different result when running this code on your computer. For me on Windows, I see the letter C:\\. I'm going to open the project panel now and copy my files directory that contains my empty file. I'll open the project folder in Explorer. I'll drop my pasted directory on my root drive at the root so that I have a files directory directly under the root. If you're trying to do this on a Mac, the root is hidden by default and may be complicated to do because of user privileges. It's not really important that you do this on your computer. It is important to understand how to access files and folders from the root. Getting back to my code, I now want to test if this file exists and not the one that's under my project directory. To do this, I can simply add a / as the first character. This indicates that this is an absolute path. To prove this, I'll print out the absolute path after I get the file instance. Let's review the output of running the program. I can see the file was found, but this time the absolute path is C:, then \files, another \, and then the file name. There are overloaded constructors for file, and the next one I want to show you takes a parent path. I'll change my file name back to a relative path by removing that first /. I'll change the next statement, and this time pass 2 arguments. The first one is another string, which is the parent path. Here, I'll pass just the root, so a single / stands for the root. Let's see what happens when I run this. I get the exact same results as before. Now I'll change that first argument to be the current working directory. I can do this by passing in a dot as a string literal. This is a common way in many programming languages to reference the current directory. Running this to see the result. You'll now see this code has found the file in the projects folder. Notice that the dot here was printed in the absolute path. This is called a redundant name element. When we get to the NIO2 types, you'll find methods to normalize the path, which removes these redundant name elements. There's another constructor I'll show you that takes a file instance as the parent as the first argument. I'll pass it the current working directory directly as the parent instead of a string literal. The getAbsolutePath actually returns a file instance, not a string. I'll run this. You now see I'm still getting the file in the projects directory, but this time the absolute path doesn't include a dot in the path. Let me summarize a few of the concepts I've covered here on a slide. A directory or folder is a file system container for other directories or files. A path is either a directory or a file name and may include information about the parent directories or folders. A root directory is the top-level directory in a file system. In Windows, this is often the C drive, for example. The current working directory is the directory that the current process is working in or running from. An absolute path includes the root by either starting with / or optionally C:\/ in Windows, where C is the root identifier. A relative path defines a path relative to the current working directory and therefore would not start with / but may optionally start with a dot, then a file separator character. These concepts will become more important as we continue to examine the enhanced functionality the NIO2 types provide. Before we move to those types, I'll put up the API for the file classes methods. Right away you can see that there are methods to check permissions of a file or directory, such as can execute, can read, can write. You can create a new file. You can delete the current file. If I scroll down, I'll see many more methods like isDirectory and isFile, which will tell me the type of path. Here's listFiles, which will give me a directory listing if my file type is a directory and so on. This is pretty familiar functionality to anyone dealing with a file system. Now let's switch to the documentation for the methods on the files class in the java.nio.files package. The first thing you might notice is they're all static, so you don't create an instance of this files class. Instead, you call static methods, passing a path instance in most cases on which it will operate. Right away I can see functionality that's similar to the file class like createFile, but here's createSymbolicLink. The file class doesn't support symbolic links, so this is an additional feature. Don't worry if you don't know what a symbolic link is. The point is, this class contains a lot more functionality than the older file class. That's true not only for file system operations, but it also gives us some additional helper methods for reading and writing files. I'll scroll down to the read methods. Here you see we have many options, like read all bytes, or read all lines. Here's a read string which will read the entire contents of a file in as a single string. This method does have some limitations, and I'll get to them later. At the end of this list, you'll see write methods here as well. This is powerful stuff, simplifying many of the jobs you'll do for basic file reads and writes. Now let's try to get a bird's eye view of the file's type. Here are the types I reference in my code from the java.nio.file package. You can see that path is an interface and not a class like the file class was. The paths class consists exclusively of static methods that return a path instance. The files class, on the other hand, has many static methods that perform operations on files and directories. This class operates on a path instance, which you pass to these methods. It has a lot of functionality in common with the older java.io.file class, but provides much more, as you saw briefly in the API documentation. When you use the file class, you get an instance with a file constructor, and then you execute a method on that instance. Here, behavior is a member of the instance itself. This is a pretty familiar pattern. If we look at how to use the NIO types to do something, we first have to get an instance of path. We don't do this directly. Instead, we use factory methods on the path class or the paths class or other types I'll talk about later. We then call the static method on the files class to do something on the path instance passed as an argument. I'll add some code to the main method that does what file.exists does, but uses the NIO types. First, I need to get an instance of a type that implements the path interface. I don't have to hunt for this type in the API docs. I just have to use a factory method to get an instance. I'll start with the factory method on the paths class, which I've set as a class strictly in existence to provide these factory methods. It has overloaded get methods on it. I'll pass a string literal, the same as I did above. Remember, this is a relative path. I'm going to copy lines 20 to 25 and paste that at the end of this method. Once I paste that, I'll change file to files in the if expression, effectively changing to a static call of the exists method, passing path to that method. I'll also just put 2 at the start of each output statement so I can tell these are from this code. Let's review what we get by running this. You'll see it found the file as it had when I just used my file instance. This doesn't seem that special, I admit. The newer code does what the old code does, so where's the advantage? For the answer to that question, you'll have to wait until the next video. I'll cover both the common functionality and the additional features available in the NIO2 types, so I'll see you in that next video.